welcome to our final USACM Energy and Earth Systems Technical Thrust Area monthly webinar, the final one for the spring semester. So we're going to do a hiatus for the summer, and we're going to restart again in September as usual. So I'd encourage you to join our TTA if you're a part of USACM. It's free. We also post all of our activities and webinars on our LinkedIn page, so you can follow that for free. And I'll just mention we're organizing our first thematic workshop in September 22nd through 24th in Austin, Texas. The title is Artificial Intelligence and Digital Twins for Earth Systems, AIDT4ES. The registration has closed for that. We actually received an astounding number of 91 submissions, which is more than we expected. But if you're interested in the workshop, I would encourage you to, even if you're not presenting, to try to attend. The registration fee is very low, so it's $150 for regular USACM members and only $100 for students. So that's my little plug that I do at the beginning. Let me now introduce today's speaker. So today's speaker is Professor Jeremy Bassis from the University of Michigan. Jeremy is a geophysicist and professor at the University of Michigan who studies ice sheet dynamics and evolution, both the past, the present, and the future. Jeremy is also the director of the Climate Impacts and Solutions program at University of Michigan, which is a Master's of Engineering program that trains physical scientists and engineering students how to work with communities and industry to apply climate information in decision-making and design. So today, Jeremy will be giving a talk entitled Stability of Ice Shelves in a Changing Climate, and I'll go ahead and hand it over to Jeremy.
Thanks, Irina, and thanks to the organizers for inviting me here. Sorry for the delay getting going. And to start, I should say that I'm embarrassed on two fronts. The first is that I realize that what I'm going to talk to you about today is part of my laziness in attempting to avoid computing anything at any cost. And I understand from Irina that this is a very computational mechanics, geomechanics type of work. And you are going to see that I'm actually incredibly lazy and avoid making any computation at any cost. And I will go to extraordinary lengths to do that. The second embarrassment, which I hope I can fix a little bit better, is that this is going to end up being a fairly technical, niche glaciological talk. But I can fix that because for the purpose of this seminar and beyond, you are all going to be glaciologists. I will give you a little crash course in glaciology, and you can then print out your card, be card-carrying members of glaciology, and roll your eyes at me and do whatever else the normal glaciologists do when I'm speaking. So to get started, what I want to talk to you about is I want to talk to you about ice shelves. And what you're seeing in this image to my left on the screen is an image taken by stitching a whole bunch of images together of Pine Island Thwaites Glacier. Thwaites Glacier is what some people might call the Doomsday Glacier. And you're seeing the ice flowing out into the ocean. And you're seeing that smooth gray stuff, whitish stuff is sea ice, and then it's starting to float on the ice, on the ocean. Those are called ice shelves. And you're seeing, if you look closely at that image, fractures, bits of ice breaking off. This is what we want to model. We want to model this complex material that's both flowing and breaking. Now, the image next to it is actually an image taken by the Associated Press of Galveston in the aftermath of Hurricane Ike. Now, sea level rise, which is what we're interested here, is never going to raise sea levels by 3 meters in 3 hours, which is what happened during Hurricane Ike and many other hurricanes. But what's happening right now is the U.S. Army Corps of Engineers is about to embark on its largest, most costly project ever, which is building a seawall to protect Houston and Galveston from future hurricanes, but also hopefully factoring in future sea level rise. So let's give you your crash course in glaciology. And what you need to know is that an ice sheet is just a gigantic mountain of ice that's fed by snowfall. As that snow accumulates on top of the ice, it starts to compact and it starts to flow out towards the ocean or the coastline. Turns out that ice is what we call a shear weakening fluid or a shear thinning fluid. And as it starts to spread out towards the ocean, eventually, if it turns it's into a deep enough ocean, we form these things called ice shelves. And these are freely floating extensions of ice that are fed and nourished by that snowfall from the grounded ice sheet. Now, the reason ice shelves are important, they don't actually contribute to sea level rise when they melt or decay because they're freely floating. But what they do is they limit discharge across the grounding line. Now, the grounding line is that region where ice transitioned from grounded to floating. And it does this whenever it can scrape along the sides or it has a pinning point that sticks up into its bottom, it can limit that flux of ice. And so when ice shelves have gone away, what we've seen is the tributary glaciers and ice streams that fed them often accelerate. And we've had some pretty dramatic examples of that. But one of the things that's interesting about ice shelves is they come in all kinds of shapes and sizes. Now, I'm going to mostly focus on the Antarctic ice sheet. And the Antarctic ice sheet is pretty much surrounded by ice shelves. So almost all of the flux from the grounded ice eventually finds its way into these ice shelves where it gets discharged. And you can see these gigantic ice shelves. These are shaded in light gray here, like the Ross that feeds into the Ross Sea, the Filchner-Ronne. But one of the things that we've also seen is that these ice shelves, like the Ross and Filchner-Ronne, can be thousands of kilometers in scale. But in addition to that, we also have these tiny ice shelves. So right next to the Ross ice shelf, which I'm showing you here on the left, you get the Erebus ice tongue, which is only 5 kilometers. So several orders of magnitude smaller. We move over to the Amundsen Sea sector of Antarctica, and what we see is these ice shelves that are maybe 50 to 100 kilometers. And it turns out that Greenland used to have giant ice shelves as well, but most of them are gone. And the ice shelves that are left tend to form in the northernmost portion of Greenland. They tend to be fairly small. We used to have extensive ice shelves across the Arctic Ocean. Almost all of those, except for a few fragmented remnants, are all gone. And that's kind of an interesting question because the Arctic Ocean and Greenland used to have extensive ice shelves, but they are there no more. And that might hint at the future of the Antarctic ice shelves as we continue to warm the ocean and the atmosphere. And in fact, over the past several decades, we have seen some dramatic changes in ice shelves. So for example, here I'm showing the Antarctic Peninsula, and the Larsen B ice shelf had been stable for maybe 10,000 years or so until about 6 weeks in 2002, when it started to form all of these melt ponds that then dug all their way through the ice in this hydrofracturing process. And the complete ice shelf completely disintegrated in about 6 weeks. So what you're seeing here is this image where these light blue areas, that's not ocean. That's actually regions where the ice is broken into these tiny pieces of ice that are smaller than the pixel size. You see these bits of ice that are floating out in the ocean. It looks like what happens is you end up with this ice shelf that became Swiss cheese, and these icebergs just started to collapse on each other in this explosive disintegration. This particular disintegration appears to be surface meltwater driven. But if we go elsewhere into the Amundsen Sea embayment, which is that original image that I showed you on my title slide, we start to see a different story. Now, there's almost no surface melt in this region. It's still really, really cold. Now, we probably don't start getting surface melt until a few centuries, maybe 150 years from now. But what we have seen is increased bottom melting. So the ice is in contact with the ocean. These regions appear to be driven heavily by the ocean. And this particular image that I'm showing you is showing the ice flowing out into Pine Island. This is one of the most rapidly changing glaciers in the world. And then we also see this Thwaites Glacier, which is sometimes known as the Doomsday Glacier. I don't think I can easily point this thing out with Zoom, but if we were in person, I could point these out a little bit easier. And what you see is that these ice shelves have started to really break up and they're heavily fragmented. So just to show you a great animation of Pine Island, that's kind of at the top of this MOAA image. What you're seeing is the ice is primarily ice shelf here, and it's flowing out to the ocean towards the bottom of your screen. You can see it's mostly sea ice free, although sea ice comes and goes. And you're seeing these shear margins where the ice is clearly starting to break into these fragmented bits. And you're seeing at the calving front this slow detachment of tabular icebergs that are causing the ice shelf to retreat. And what we're seeing now is these tabular bergs appear to be detaching every few years. A few decades ago, they were detaching every few decades. So we've seen a process that is now accelerating. So you're all card-carrying glaciologists now. And so I am going to ask you a question. And when I say go, you are going to enter this multiple choice question into the chat. Now, my guess is that none of the chat's going to be saved. You don't have to worry about having your answer saved for posterity. But we do know about how many people on here, and I'm sure Irina is going to glare at anybody who chooses not to answer. And so the question is, as glaciologists, when do you expect global sea level to exceed 1 meter? And once I say go, I'll ask you to enter your chat, your answer. But the first is 2050, 2100, 2150, after 2150, or never. So go ahead. All right, so we're seeing everyone entering their values into the chat, right? And one of the things which we could do if I was much better at technology, which I'm not, is do a little histogram of people's votes. But if you scroll through the chat, you can see people voting for a handful, maybe by 2050. A lot of people are suggesting 2100 or perhaps by 2150. There's a handful of people that are suggesting it will never get that large. And so what we can see is a complete distribution of folks with different opinions on when we expect global sea level to exceed 1 meter. This is kind of the problem that I've been focused on for the past 2 decades, is can we actually narrow that down a little bit more? And so it turns out that actually everyone is right, depending on which scenario we choose. So what I'm showing you here is sea level projections, global sea level projections from the US Interagency Sea Level Report. And so by 2050, the higher end of our estimates are about 25 centimeters. By the time we get to about 2100, we're starting to look at the higher end of about 1 meter. But there's also a low end estimate as well. That's maybe a few tens of a centimeter. And so what we have is what we might call high end and low end sea level projections. And the high end corresponds to more aggressive emissions, but also we're not quite sure what those emissions are going to do to the atmosphere and ocean forcing. So those correspond to also fairly high levels of warming in the ocean that then cause cascading feedbacks. And you'll notice that by 2050, there's not a lot of difference in what the ice sheets or sea level is likely to do. And that's because a lot of that sea level is really already baked in. It turns out that we've already committed ourselves to a few tens of centimeters just from the emissions we've already had. As we go out further and further into the future, those scenarios end up being more and more uncertain. Now, the question is, what timescales are important for you? And everybody can have a different answer to that. I have talked to people in the planning community that are really focused on the next 2 to 3 years, possibly 5 years, maybe out to 10 years. The 2 timescales that I have found most interesting, both from a personal and adaptation and communication level, are one, which I'm going to call the Back to the Future timescale. So Back to the Future is a movie that took place in 1985. Marty McFly went back about 30 years. Those of you who are millennials or younger, ask me about this later. And it turns out that if Back to the Future took place today, we would go back to 1995. I can see some of you are shutting off your cameras, which makes me think that maybe you are going to have to go lie down for a little bit. If you're also into television from that area, the Wonder Years, if it took place today, would take place in about 2005. These are interesting timescales because we can imagine what our future life would be. If you remember Back to the Future 2, they go into the future by another 30 years. It's a timescale in which I hope my kid has grown up, gone to college, started his own life with perhaps his own family, but I'm still alive to see it. The other timescale that I often focus on is what I call the intergenerational timescale. And everybody's going to have a different set of timescales that they care about the most. This is a timescale in which the ice sheets really start to change a lot. My son is currently 13 and my father is about 83. So that rough 75-year timescale is what I call the intergenerational timescale. The coastline that I remember going to as a kid is one that will no longer exist for my son when he takes his kid to the beach. But it will exist in our intergenerational memory. All right, so the rest of the talk, now that you guys are all expert glaciologists, is going to focus on how we understand what's going to happen. And it turns out the key to understanding which of those scenarios we're on is really emissions. Forcing is the second thing, which forcing path we're on. And the third thing, which I'm going to really focus on today, is the mechanics of what happens to these ice shelves. So I'm showing you a conceptual diagram that we put together for a review paper last year. And on the left-hand side of this diagram, you have this rapid explosive disintegration of like the Larsen B. The meltwater driven, the ice shelf completely explodes. The area increases, actually an energy producing gravitational potential energy is released. In the middle of this, we have a timescale that's more like months, and we get sustained calving of icebergs from places like Thwaites, Pine Island. It's kind of steadily detaching ice, retreating as well. And then the final one that I have on the right is the longer timescale, which is most ice shelves break off these big tabular bergs every 30 to 40 to 50 years. And there's nothing particularly alarming about that. It's just what we expect from the regular behavior of ice shelves. The question is that will that process accelerate, slow down, and that affects ice shelves. So if we want to understand this, we have to really try and understand the intersection between how ice flows and how it breaks. And this figure that I'm showing you on the left is a zoom in of Thwaites Glacier that I love from a Liz Logan paper from 2013, which really shows all of these surface features that you're looking at. And as you get into the ice shelf, you get what I call this chiclet style of fragmentation. It kind of looks like these chiclets, these little tiny icebergs, although they're not that tiny, they're kilometers in scale. And it's kind of this regular pattern. If we go to the Larsen C ice shelf, that's over in this Antarctic peninsula that I talked about earlier, we can see in almost every ice shelf these patterns of basal crevasses. These chiclet styles probably start as basal crevasses that eventually get all the way through the ice thickness. And in this figure here, we see these beautifully resolved basal crevasses that are not narrow, brittle features the way we used to think about them as terms of linear elastic fracture mechanics. These are basal fractures that extend hundreds of meters into the ice thickness and are hundreds of meters wide. Lots of ductile flow happen to make this ice crevasse look the way it does. And to try and link this to melt, what we're also increasingly seeing is observations that show Pine Island, Thwaites, these glaciers I was talking about, are increasingly getting forced by the ocean. I'm showing Petermann, which is Greenland, which is one of those other ice shelves that exist in Greenland, one of the few. And these are developing these melt channels where the melt becomes localized beneath the ice shelf. And what Karen Alley pointed out is that we end up with these really large melt rates in the margins. And these seem like they can nucleate rifts that propagate all the way across. So it's possible that basal melt, and fracturing are linked along with the evolution of the ice. So things that we've been working on for a while is a former student, Ray Watkins, noticed that if we look at the roughness of the ice, how bumpy it is essentially, it seems like that roughness is pretty well correlated with basal melt. The higher the melt, the bigger the roughness. And the problem that we've been facing is that it turns out that all of our ice shelf models that we put in, no matter what roughness we start with, they all smooth out eventually. And it turns out that the bigger the melt rate we put in, the faster that smooths out. And so for today, I want to talk about really two questions. And the first question is, why are ice shelves so bumpy? And of course, the corollary to that, why we care about that, is we want to know what this tells us about ice shelf stability. The second question, which is very much related, is why does basal melt increase the bumpiness of the ice shelves? And why is it seeming to make ice shelves less stable? And then, of course, bigger picture is, what does this tell us about sea level rise? So the starting point for this is a paper that Yue Ma and I wrote back in 2015. And it's kind of a paper that I've always liked because I started the paper when I was a graduate student a decade earlier, around 2005. I got stuck, couldn't make any progress, came back to it a decade later. And what we proposed was this conceptual model in which you pull the ice shelf apart, you get these crevasses, and they're initially probably pretty narrow. As you pull the ice shelf apart, you can get plastic necking, which can widen and deepen these crevasses. Because the forces have to be equal along that whole section, it turns out you can get stress amplification. But that whole process is going to be modulated as we come down this figure by cold ocean, which could fill these crevasses with marine ice. That's refrozen ice in the bottom. Or you could potentially imagine if the ocean is really warm, we can excavate them. And so this allowed us to link crevasse growth with ocean melting. But we had a couple of problems with this. And the basic idea behind our approach is we did a linear stability analysis. We can take an extension of ice. Turns out everything depends on this non-dimensional number S, which is just the ratio of gravitational restoring force to the extensional deviatoric stress. We could decompose perturbations into normal modes and then sort of solve for the perturbed velocity, growth rates, blah, 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 blah. And it turns out that if S is this non-dimensional number is less than 1, you get growth. If S is greater than 1, you get decay. And melt can increase that growth. We did some simulations all the way back in 2015 of what this might look like for a trajectory of ice that was advecting through the Larsen B ice shelf. And what you see is we eventually get full penetration. We get these wide crevasses with kind of this narrow top to it. But we had two really major problems. First is, or the zeroth order problem, is that this predicts the ice shelves are way too stable. Second, we needed to initialize damage. We need to put that narrow crevasse in there somehow. But perhaps the most substantial issue is we did a linear stability analysis. So it's really restricted to infinitesimal amplitudes, and the amplitudes are almost never small. So this dashed line that you're seeing in the bottom figure is actually how we initialize the damage. It was typically somewhere between 0 and 0.5 ratio of the thickness. And just to back up, when I say damage, what I'm really going to mean is the ratio of crevasse depth to the ice thickness. It's not really damage the way we talk about in continuum mechanics. It's really just crevasse penetration depth ratio. So we needed to figure out a way to add damage into these ice models, and we needed to figure out a way to initialize the damage in the ice models. And it turns out our choice was to use this old-fashioned calculation by John Nye from 1955, who argued that crevasses are going to penetrate to the depth where the horizontal stress vanishes. And this figure on the left is going to show you this Nye depth, and S is the stability number. If it's 0, it means that you're really pulling hard on the ice. There's really no gravitational restoring force. As S gets larger, it means that gravitational restoring force is larger than the extensional destabilizing force. Roger Buck, in the past year, has come off and said that, in fact, that approximation assumes that the ice is infinitely thick. If we take into account the finite thickness of the ice, we get a different answer that results in much deeper penetration of crevasses. And of course, other people have used linear elastic fraction mechanics, phase field methods, damage mechanics. But what's interesting about Roger Buck's force balance analysis is that it turns out that a freely floating ice shelf, in which we have plenty of examples, has an S of about 2, and every ice shelf is required to have an S of about 2 near the front because of the boundary condition. And so Roger's analysis predicts that ice shelves should not exist. As a glaciologist who's actually spent time camping on ice shelves, that's a bit of a problem from a theoretical perspective. And so one of the things that we wanted to figure out is, well, what is going on? What should we initialize damage to? How deep should crevasses go? And even though we have very few observations, we wanted to see if we can figure out why Roger's prediction doesn't actually seem like it can hold for ice shelves. So we wanted to get around this whole initializing it and trying to figure out something that can reconcile our estimates that use a full force balance and conservation of momentum. And the way we did this is we decided to extend our linear perturbation analysis all the way up to a weakly nonlinear, and we're going to extend it to fifth order. So unlike a traditional linear stability analysis, you look at the stability of each mode individually. This gets super cumbersome as we start to consider more and more modes. And it turns out that every time you go to higher order, you get higher order harmonics. And so the expansion quickly becomes extremely difficult. So this was essentially the project that I was working on for about 5 or 6 months of my sabbatical, was trying to figure out exactly how to do this expansion. But what's neat about this is that we can use this weakly nonlinear extending all the way up to fifth order to try and come up with a stability diagram. And I'm going to take you through this stability diagram in quite a bit of detail because I'm going to show you a bunch of diagrams that look pretty similar. So on the x-axis, you're seeing the stability number S. So a stability number of 2 means freely floating ice shelf. Stability number greater than 2 means that there's some buttressing, some restoring forces from pinning point sidewalls that's reducing the extensional stress. And a stability number less than 2 means that there's some kind of stress concentration in the ice shelf. So it's flowing around something sharp that's concentrating stress. This happens, for example, in the shear margins of ice shelves that I showed you earlier. So on the left axis, I'm showing you damage. Now, what damage is essentially the ratio of perturbation to ice thickness. And our approach here was to look for what we call quasi-stable solutions. So these are slowly evolving solutions. And the brown and black line basically plot on top of each other. Those are showing you the results for different types of Glenn flow rheology. One is Newtonian, the other one is non-Newtonian with a flow law exponent of 3. And so this dashed line that goes up is a stability contour. So as soon as the perturbation amplitude exceeds that, we expect the perturbation will become unstable and propagate all the way through the ice thickness. If you have an amplitude that is less than that, you will decay all the way to 0 amplitude origin. So the shaded red regions are showing unstable portions of this curve, and the blue regions are showing stable portions. So first off, low amplitude perturbations decay to 0 for S greater than about 0.9. This is arguing that basically, unless you're really pulling hard on the ice shelf, all of your perturbations are going to decay. If you get really big perturbations somehow, the amplitudes are going to can eventually become unstable, but again, only for high amplitudes. And in fact, at the freely floating limit of S equals 2, all of our ice shelves are going to look pretty stable. So we can actually show you what this looks like. So if we were to do an animation of what this ice shelf would look like as the amplitude of the perturbation evolves, and I'll show that again. what you see is this decaying perturbation in the blue space if we initialize there. We can alternatively initialize in that red unstable space. And here we see these crevasses that are growing. And what's intriguing about this is we have these crevasses that are growing with a wavelength of multiples of the ice thickness. Now I'm showing you this result for a single wave number. We can go look at other wave numbers. So this is K is equal to pi h. H is the thickness over 2. So we're starting with wavelengths that are about twice the ice thickness. And again, just to emphasize, we can start near that transition and we get these crevasses that are roughly stationary in the ratio of penetration depth to ice thickness. Now, I just realized that I forgot to talk to you about the one thing that I was supposed to talk to you about, which is the numerical methods that we used. So going back to this earlier slide, these red circles with the error bars, we verified this the analytic calculations using a full Stokes model in which we can initialize damage with any perturbation that we wanted for any amplitude and allow it to evolve. And you'll see that our numerical simulations actually agree pretty well with the weakly nonlinear. As we extend to higher wave numbers, the agreement is pretty good. You'll also notice that I'm plotting that Nye model for how deep perturbations or crevasses should go and Buck's force balance model. And they do intersect right around S equals 1 for the Nye and then at around S equals 2 for Buck's force balance. But our interpretation is different. Our interpretation is that if you have any perturbation that is less than that depth, you're going to decay to 0, and anything larger will grow all the way to the ice thickness. So we could potentially argue that some of those are actually starting to overlap. As we get to higher wave numbers, again, increasing the wave number to be about proportional to the ice thickness, we're actually starting to see the analytic weakly nonlinear solution and the numeric solution starts to diverge pretty heavily. And what's interesting here is we can no longer trust our weakly nonlinear, but the numerical solution is starting to show hints of a different type of behavior, where actually, if we look at this little bend in the numerical values, what we find is anything that is above the lower branch grows to the higher branch, and anything above the higher branch decays to the higher branch. So we're actually finding for high wave numbers where we expect our weakly nonlinear analysis to start to break down, high amplitudes, we start to really see that there's actually a stable branch that is starting to emerge from the analysis. All right, we can go to even higher wave numbers. And here our weakly nonlinear analysis completely breaks down. But what's interesting about this is we really start to see the emergence of a stable branch where the origin, 0 perturbation, starts to become increasingly unstable. And perturbations that are, once they're above a small amplitude, grow to this stable branch that, intriguingly enough, seems like it lies between Roger Buck's and the Nye model. In fact, if we look at that with a little bit more detail for a bunch of ice wave numbers growing out higher and higher and higher, we find that this is actually true, that the higher the wave numbers, the lower the lower branch starts to approach the x-axis. And we find that we end up converging for higher amplitude or damage at this value that's somewhat intermediate to the Nye and Roger's force balance argument. So Roger, I think, was actually mostly right, but his approximation seems like it is starting to break down as you get to higher and higher amplitude damage. And so for us, we find that with these numerical simulations, the freely floating ice shelf case is stable, but damage can actually grow pretty large to close to 80%, 78% of the ice thickness. So it does seem like we're converging towards this stable solution that is a bit shallower than Buck, but deeper than Nye. And so that helps to reconcile that difference. We can also add melt. So here I'm showing you a set of wave numbers that are on the long side. And again, you're seeing the exact same type of stability. And in this case, melt is non-dimensionalized by ice thickness times the strain rate. And the bigger the melt is, the less stable things are. So once we start adding melt to our initial simulations that had no melt, you start to see that freely floating ice shelves start to become unstable. As you start to crank melt up further and further and further, everything becomes unstable. The other thing that you can see is that for low amplitude, our weakly nonlinear agrees pretty well with the numerical, but as the amplitude gets larger and larger, we're seeing an increasing divergence, so that our weakly nonlinear analysis really starts to become a problem and less accurate for higher and higher amplitudes. We can see similar patterns if we go to a higher wave number. Again, we see good agreement for low damage amplitude and agreement that increasingly diverges. But what's interesting here is, again, for any given value of background melt, we can push any ice shelf into an unstable regime. This isn't really accounted for in Roger Buck's or the Nye criterion, which would be largely independent of melt rate. All right, so you're all glaciologists, and this has been super technical. So what I want to do is to come back and actually just show you what this looks like for a simulated set of ice shelves. So what I'm showing you in the left and the right of these figures are the Amundsen-Sea ice shelf. So at the top, you've got Pine Island. As you go down in a clockwise, you get Thwaites, and then Dotson Crossan. And on the left side of this, I'm showing you what we would predict from this original Nye. That's how we initialized our model initially. That's what a lot of people are still using. And you see localization of damage in the shear margins. But a problem for us has always been that you get actually damage pretty much everywhere in the ice shelf, even where regions where it's pretty intact. It's just at a lower level. If we use Roger Buck's force balance, we find out that all ice shelves everywhere are unstable. So this is an extreme case. Now, if we use our own weakly nonlinear put it into this model, and it was actually Sam Kachuk that produced this output that I used for these calculations, and we're using the bicycles ice sheet model, which is developed by the DOE, then what we see is our weakly nonlinear produce a very different type of behavior. And the weakly nonlinear analysis suggests that, yes, you have a lot of damage in places like Thwaites, but Pine Island, kind of similar to what we see from the surface observations, most of the damage that we expect to see is actually highly localized in the shear margins. If we come back to this original animation that I showed you, what we're seeing is these highly damaged debris of ice in Pine Island shear margins as the ice flows. As we get down closer to the calving front, we're eventually getting these rifts that are developing. We're not getting that in this particular model, although this is just a stationary single time step of the model. But we're getting this high localization right at those shear margins. Now, these simulations were done initially without melt. As we start to increase melt, we start to see larger and larger damage, roughness, whatever you want to call it, spread across the ice shelf. And so once melt exceeds a critical amount, you're pretty much seeing large damage localization across the entire ice shelf. Now, just to be clear about what I'm showing here is we are assuming a single value of melt, not a value of melt that varies over the ice shelf. And what's more is we're assuming that this is reaching a steady state in terms of the crevasse or perturbation or damage evolution, which is almost certainly not the case. But this is important because that damage evolution timescale can be somewhere between 10 years to a century, depending on the ice shelf and the kinematics. So to leave you with one final point, this map on the left is melt rate of ice shelves. The reds are lots of melt. And we've seen a lot of our ice shelves already undergo this transition to being high melt environments. As climate continues to change, under current emissions, we expect more and more basal melt so that more of these ice shelves that have the light blues in them will start turning darker and darker shades of red. It turns out for a lot of these ice shelves, according to our own calculations, they've already potentially reached the stage at which they may be transitioning to an unstable ice shelf. However, because the time scale is on the order of 50 to 100 years for a lot of them, it's possible that that evolution is something that will play out in the future. And with that, I will stop and take a few questions now that you are all expert glaciologists. And at least according to these simulations, we are starting to be able to resolve some of these things that we've struggled to for a long time in terms of shear margins and rifting. So thanks very much.
Thanks a lot, Jeremy. This was great. So normally I say to clap, but I think there's an emoticon for that. So let's see if I can push it. Are there any questions for Jeremy? So I can start. Yeah, I was curious at the beginning when you were showing that upper and lower bound, like the upper being 1 meter by 2100 of sea level rise, and the lower one being a few centimeters. Was that under the? I guess the top one was RCP 8.5, and the bottom one was probably the lowest emissions. Are those the scenarios that were used for these analyses?
Yes, it's a little bit more complicated than that because the high-end scenario is RCP 8.5, but also some of the more extreme model responses to that one. So it turns out that if you feed a bunch of ice sheet models different scenarios, they have pretty different responses sometimes. And so the low-end scenario is a very low emission scenario, but also relatively unsensitive ice sheets.
Okay. Questions from the audience? Check the chat here.
Looks like Rupert's raised their hand.
Yes, sorry about that. I was looking around. Yes, Rupert, what is your question?
All right. Hi. Thank you, Jeremy. It's great to finally become a glaciologist. I had 2 questions. So maybe I'll ask one and then see if other people want to ask a question rather than hogging the floor. So if I understood right, the melt, when you add melt, this is a uniform melt rate. And I just wondered what you thought, how big an impact you think it'll make if you have either preferential melting at the deeper parts of the ice base or in the apex of channels, both which could happen depending on the oceanographic conditions.
Yeah, so that's an excellent question. So we just assumed a essentially background melt rate that we could then add into the analysis. The question really is, of course, the topography of the ice as it evolves will affect the melt rate. And so you could potentially have both positive and negative feedbacks. So our analysis for melt rate, we really kind of kept it to the larger wavelengths and avoided the much smaller wavelengths where all kinds of really complicated stuff could go wrong. So the short answer to that is I actually think that would affect things quite a bit. I think what you're going to find is that if we assumed a melt rate that depended on the topography with the pressure melt point, that is actually going to result in a somewhat less extreme result sensitivity to the melt. But I also think you're going to find that there's a sensitivity to the slope. So I think what we'd find is that you tend to change the shape in addition to the amplitude because the slope would end up being a dominant contributor. But that would also depend on actually figuring out a little bit more about the ocean. So what we could do and what we should do is linearize an ocean plume model and couple it with our linearized solution to the ice part of the problem. I hope that answered your question.
Yes, thank you.
So Roger Buck has a question.
Hey, Jeremy, Roger here. So I keep hoping that going to talks like this, I will inch closer to actually being a glaciologist since
you're all glaciologists now, whether you like it or not.
All right, well, let's hope so. So no, the one thing that I've always thought about these the nye stuff and then what I did, super simplistic kind of approaches. But I've always thought that, fracture toughness and or tensile strength has to enter these things in an important way to make, like you were saying, floating ice shelves can be stable.
Yeah, I mean, if you look at the scaling, by the time you're fairly deep crevasses that are hundreds of meters, the fracture toughness doesn't really play that big of a role. It's not that bad of approximation to assume that the ice has no strength. For small crevasses, it plays a really big role. And so that might be the factor that is preventing crevasses from going all the way through. The other factor that I think is worth thinking about is if you do have a crevasse that is trying to penetrate the entire depth, for the most part, the ice is very, very cold. And so what might very well happen is if the ice is not straining fast enough, you're just going to freeze that crevasse shut faster than it can propagate.
I agree completely. Yeah.
Thanks, Roger.
Let's see. Other questions? Did you want to ask your second question, Rupert?
Yeah, go on then.
There's-
So this is just a very simple one about whether I was interpreting your plots right. If you go back to the last plot you showed with damage for Pine Island Glacier and friends, where on the right-hand side, in the high melt scenario, you have more damage. So yeah, this one. I was just a bit confused because for Pine Island Glacier, it looks like the shear margins themselves are the whitest part, which is the lowest damage. So what am I misunderstanding?
Yeah, that's actually because I played a little bit of trick in how I plotted the higher melt case. So it turns out that that those regions, there actually is no solution whatsoever except for penetrating all the way through the ice thickness. So for a lot of the other simulations, I actually calculated a steady state. This one, I didn't quite make it all the way to steady state. And so those are actually evolving. So you start with a small damage, it will eventually make it all the way through. So the white areas will eventually become red, but I played a little bit of a trick by not going all the way to steady state for this particular one.
Okay, cool. Yeah.
But that good eye.
Let's see. Other questions?
Daniel?
Oh, yeah. Thank you, Jeremy, for the talk. I have a question about your stability plots. How sensible are these curves to the ice temperature? And what assumptions did you make to calculate this stability? Because I wondered, it could be highly sensitive to the value of temperature in terms of fracture. Maybe you could say something about this.
Yeah, that's a good question. So the biggest assumption that we're making actually is we're ignoring any vertical temperature dependence. And that could actually have a fair-sized effect. The other thing where it enters is, of course, the stress. And so the effective temperature is going to map itself very differently on different melt rates because it's really how quickly can you melt versus how quickly the ice can flow. So that's kind of a balance that's happening. And that's why the non-Newtonian case where n is equal to 3, the ice is actually trying to flow in and trying to close those crevasses faster than the ice can melt it. So that temperature really has a really important effect. We can remove that effect by considering non-dimensionalizations. But what I haven't considered here, although we've looked at it in a couple of different ways, is what happens if the ice is much colder at the surface and much warmer at the bottom, because the bottom is, of course, in contact with the ocean, so it has to be the pressure melting point. And the surface is going to be kind of minus 20, minus 25 degrees. And so that will actually have a change in the dynamics of how these instabilities grow. But we haven't really explored that in all that much detail yet.
Thank you.
So I guess I can ask maybe the final oh, Rupert, do you have another question? Go ahead.
Yeah, sorry, I'm always a troublemaker. I just
It's great.
I'm always too much to ask about. So, but much more generic question, Jeremy.
Mm-hmm.
If you want to do a good job of representing the detailed processes of an ice shelf in a large-scale model, what's the simplest approximation to the Stokes equations that you can get away with? Let's say you're going to add a representation of damage, maybe along the lines of what you've suggested, but if you're starting with something as simple as, for example, the shallow shelf approximation, can you do a good job with that?
Yeah, I mean, so I don't know that I have a satisfying answer to that, because I think that the honest answer is we don't know, right? So the shallow shelf approximation that Rupert's talking about is the common assumption that we make in a lot of ice shelf models, which is that we can ignore small wavelength features, and small being small compared to the ice thickness. Now, that works really well for the large scale dynamics of the ice when we start to think about features like crevasses that are clearly very small compared to the ice thickness and wavelength. Then it's a little bit less clear that we can simply scale those away. So I suppose I think that there's a number of different approaches. Different people have different approaches to this. What we've been thinking about with Matt Hoffman and others has been, we're going to stick with the shallow ice approximation or the shallow shelf approximation because that's computationally feasible. How can we add the high frequency, the short wavelength behavior back into that model? And so the weakly and linear analysis allows us a way of superimposing that in an approximate form on top of the long wavelength approximation. So we do get the high frequency behavior that we can then add back in. So that's been kind of our approach. There are, of course, if you talk to Ravindra and others who are doing very detailed numerical modeling of, the small centimeter to meter scale structure. And I think that that's valuable too. And then how do you extrapolate that to the large scale becomes another question. So the answer to your question is I have no idea.
Thank you very much.
Yeah, my question was actually kind of related. I guess I mean this is kind of getting into things that I know you work on that we didn't really get into the talk about the modeling part, but I know sort of like, I mean, traditionally you have these fluids only models like Stokes or first order Stokes or whatever, where the way that the calving is modeled is very, very crude. You just sort of, it's based on this thickness criterion. And I know you've recently been looking at introducing damage to improve that. I was just curious if you may not have slides, but sort of like, how much do you win with your damage-based approach relative to the very crude calving representations in the fluids only models for some of these glaciers that you showed, if you were to do like a hindcast and compare the simulations to observations?
Yeah, that's a good question. I mean, so what we're doing here is trying to arrive at a better damage evolution model that we can then evolve forward in a shallow shelf approximation. We're not at the stage where we're predicting the calving front position quite yet with the weakly nonlinear. We've done it for the linear approximation, and the reality is it's too stable. Calving fronts want to go too far, and so this is one of the motivations for introducing the higher order terms. One of the things from our approximation is that ours isn't really a damage mechanics formulation, because it turns out that the effect of topography is actually quite a bit different in our weakly nonlinear than what you get from the typical 1 minus d times rheology that you get in continuum damage mechanics. And that is because we are fully accounting for the stabilizing, restoring forces associated with water or air filled or crevasses. And that's a little bit of a very niche point, is that people make different assumptions about what density is filling crevasses.
Yeah, okay, thank you. Well, we're at time. So thank you everyone for coming. I think we might have had a record number of participants today, actually. So we're not going to do the webinars again until September. I'll start advertising them during the summer. I hope to see some of you at USACM in Chicago in July. We will have a business meeting there that people are welcome to join. And I hope to see some of you at the AIDT4AS workshop that I've been advertising at these webinars. Thanks, everyone.